right, our next speaker is Professor Gregory Fiete from from Northeastern University. He'll be telling us about flow-cave driving.
Let's see, how do I activate the, oh, there we go. Okay, great. First of all, I'd like to thank the organizers for giving me the chance to speak here. And secondly, I would like to thank Alan McDonald. So for those who may not know, before I joined Northeastern University 6 years ago, I was at the University of Texas at Austin for 10 years. And at that time, Alan was my mentor. So he played no small role in hiring me at UT Austin or helping me in various ways along the way. So since I haven't had a chance to speak in a conference since COVID that Alan was present, I kind of wanted to give a public thank you to Alan for all the support that you've given me over my career in ways that I know and ways that I don't know, as well as supporting my family in various ways. And I think Alan knows what I'm referring to there. So for this talk, I'm going to discuss light interacting with matter in various ways. So I'm going to look at it from the perspective of light that is changing the property of the material, as well as light as a way to probe the properties of material. And things like quantum geometry, et cetera, are going to play a role in some various parts of the talk. So an outline is roughly this. I have a number of different topics, so I'll kind of just touch on them briefly. Anyone who has questions about any of them, wants to go more in depth, please catch me in the break times or at dinner or lunch or breakfast, whatever it might be. So the first part, I'm going to talk about nonlinear phononics. I'll describe a little bit about that in the next slide, but the idea is that you use low frequency, high intensity light to selectively excite phonons. And you excite them beyond the harmonic regime, so that, say, IR active phonons are excited to large amplitude, and then they couple nonlinearly to other modes, particularly Raman modes. Those Raman modes then experience a shift in the positions about which their equilibrium oscillations occur. There's a transient structural change in the material, and that can lead to changes in the magnetism as well as electronic and magnonic band topology. So that's going to be the first topic. In the second one, I'm going to look at nonlinear optical responses where light is used as a probe. I'll focus on Weyl systems, and I have a few key results here that are related to the quantization of the injection current that's measured, the circular photogalvanic response, and how the quantization is sensitive to the way in which the bands are modeled, particularly whether you use a few band or many band system. Seems like it's well connected. And then I will look at the nonlinear optical response of a superconductor as a probe of topology. So there's, we've heard a lot about superconductivity earlier today, and there's of course an interest in topological superconductivity. It's difficult to have a smoking gun signature of topology in superconductivity. And so I will describe a nonlinear optical response as another probe that can help support the case for a topological superconductor, at least in the one example that I'll discuss. And then I'll talk about ABC rhombohedral graphene under a displacement field as a probe of quantum geometry through the nonlinear optical response. And then finally, I will talk a little bit about chiral phonons in this material. There's a typo that's cobalt titanate, titanium, oxygen 3, which is interesting. It has magnons with like Dirac-like band features, in addition to these chiral phonons that exhibit a very large splitting in magnetic field. So their G factors are quite large, and that's part of the reason for the interest in that material. Okay, so the idea of nonlinear phononics, as I mentioned, if one has a system with inversion symmetry, there are IR and Raman modes, and the IR modes couple linearly to light, first order process, and typically these IR modes are higher in frequency than Raman modes. So for example, in this plot here, you have fast oscillations in the IR plane, if you will, versus time, and slower oscillations in the QR, the Raman displacement, is a function of time. So the IR modes are fast for the Raman modes. So you can think about computing a time average over these IR modes and then asking what the effective potential is of the time averaged IR modes on the Raman modes, and they lead to a shift of the potential of these Raman modes so that their lowest energy configuration is different than what it is in equilibrium. That's shown in this dotted curve. And then the black curve, the solid one here, is the shift that the potential feels as a function of these IR modes being activated. So you shine light on the system, say with the pulse of light, and whatever the lifetime of these IR modes is, for that lifetime of those phonons, you'll experience this transient shift in the system. And then we basically model it with a sort of frozen phonon approximation, where we look at what are the properties of the system assuming this kind of structural transition. And so we looked at two different materials. So this chromium triiodide has been of interest for various reasons. We're interested in it because the exchange between these two layers, the interlayer magnetic exchange, is rather weak. So the equilibrium configuration is to have fully polarized layers, magnetically speaking. So each layer is ferromagnetically ordered, but the coupling between the two layers is antiferromagnetically ordered. So overall, the system has zero moment, but with a relatively small field on the order of a Tesla, or a relatively small gate voltage on the order of a few volts, or with a significant amount of pressure, you can actually take this equilibrium zero moment state and fully polarize it into a ferromagnetic state. So these three experiments tell us that the interlayer magnetic exchange energy is not too large. And we might be able to switch it with this nonlinear phononic process. And so we sought to see if that's possible from the theoretical perspective. So you might ask, well, why do this? If we can already do it in three ways, why do we add a fourth way? Well, the time scale associated with these is much slower than you can get with a pulse of light. So we were also motivated by dynamical changes in the magnetic properties, which could be very rapid. And this was meant to be kind of a test case for more broad phenomena that one might be able to achieve. You have a lot of control over laser properties with frequency, intensity, polarization, pulse shaping, et cetera. So there's a lot of scope to manipulate quantum materials with laser light. So this was meant to kind of be a test case for that. There's two components to the study. So one component is based on a symmetry analysis. So you analyze the crystal structure, and you can write down a potential for the deformation of the lattice, which includes the normal harmonic terms for the infrared modes and Raman modes. And then there are anharmonic terms for Raman modes individually, as well as coupling between the modes. And so in order to make further progress, you need to collaborate with people who do first principles calculations, which we did. And then they can compute what are these frequencies, what are these anharmonic terms, and also verify that the symmetry written form of this potential is accurate in terms of fitting the energetic landscape of the material. So we went through that process, and we computed in addition something which is called the effective charge, which says how strong a particular mode is coupled to the light. Up here, it's a little bit difficult to see, but there's kind of three highlighted IR modes. Down here, it's a little difficult to see. There are highlighted Raman modes. And it turns out that of these Raman modes, one of them couples most strongly to the IR modes and experiences the biggest displacement as a function of the electric field in the laser that's driving the IR mode. So that's the one here. It exhibits the biggest displacement. This corresponds to a shear mode between the two layers. And one can look at the magnetic exchange, some equilibrium value, and then a piece which is proportional to the shear. So the displacements that one can achieve are very small compared to the lattice constant. They're on the order of a few percent, just like lattice strain. I mean, you're only able to strain materials by a few percent at most before the material starts to reorient into domains or something of that sort. But that's sufficient. to change the sign of the exchange interaction between the two layers. So the main result here is that you can switch the interlayer magnetic exchange in its sign from antiferromagnetic to ferromagnetic through this nonlinear phononics regime. So the next thing we did is look at this other material, manganese bismuth 2 tellurium 4, or antimony substituted for the bismuth. This material was interesting because of candidate topological properties in the band structure. Its magnetic properties are very similar to chromium triiodide. A bilayer system has polarized layers, antiferromagnetic coupling between them. One can go through the same sort of symmetry analysis to write down the potential for the phonons for both of these materials, use first principles to compute the coupling constants, identify a particular mode that is most responsive to the driving of IR modes, and the final result is very similar, that you can get a sign change in the interlayer coupling, so you can drive the antiferromagnetic bilayer into a ferromagnetic fully polarized state. And in addition, there is a band transition that goes along with it. So at the gamma point, there's a band inversion and a change in the Chern number of the system. So this system has a topological band transition that goes along with the transition from the antiferromagnetic to the ferromagnetic state. The material is also well known for having various anti-site defects, and it turns out when you take that physics into account, it actually helps in the sense that it lowers the electric field strength of the light needed to produce that switch in the interlayer magnetic exchange. Okay, next topic, looking at light as a probe of the system. And here, of course, there's a lot of interest in quantum geometry. And so there is this quantum geometric tensor whose real part and imaginary part contain different pieces of information that appear in different sorts of responses. The imaginary part, which is the Berry curvature, is very well known, very well studied in the community. Chern numbers are derived by integrating this over the Brouillon zone, and it appears in other contexts as well. The real part of this tensor, this quantum metric, is a little bit more subtle and is more difficult to have sharp experimental signatures. So, Chern numbers you can measure through quantized Hall effects, for example. I'm not aware of any quantized response related to the quantum metric. If someone knows a quantized response, I'd be happy to know it. So, but it nevertheless has an impact on various properties. So, we looked at the photogalvanic effect, which is a DC photocurrent that's induced by light in a system that has broken inversion symmetry. There's typically two dominant contributions, a shift current and an injection current. So if one is computing the response of a system, one needs to include both of those. And as motivation, there is this set of experiments that was proposed to look at a system, a Weil system, which has both broken inversion and broken mirror symmetries, which creates an imbalance in the energies of the Weil nodal points, so that one can be shifted below the Fermi level, the other above, so that optical transitions for low frequencies are Pauli blocked, and so you essentially isolate the optical response at one Weil node. And so what Joel Moore and collaborators calculated is that you expect a quantized second-order response in this quantity here, essentially a difference in currents that are induced between right and left circularly polarized lights. So it was a nice example of a quantized response in a system which is not pure Chern number, and it's also higher order. So Chern number is a linear response. This is a second-order response. So experiments were done on some materials. So this is this ruthenium silicon material. Ideally, this would be quantized. It looks like it kind of wants to be quantized, but it's not a very, aesthetically pleasing quantization if you're used to looking at quantum Hall effects, for example. And then there was some activity on the theory side. Well, what is responsible for the breakdown of the quantization? Is it disorder? Is it interaction effects? And so we were partly motivated by trying to understand that question, as well as understanding a little bit better what sort of information about the quantum geometry is contained in these higher order responses. So just to give you a sense of how the quantum geometry is manifest in these responses, so a DC current response is coming from two powers of the electric field at opposite frequencies. So the net frequency is 0. There are these two contributions, shift and injection, second order tensor. So there's 3 indices. And there's an integral over the Boron zone, some joint density of states for energy conservation, and then these R's, which have subscripts and superscripts on them. M and N are band indices, so there are terms which are mixing bands, transitions between the bands. There's also components that are intra-band, so this is kind of like components of Berry curvature, for example. So you can see from the formulas that it's kind of all convolved together. You're integrating over stuff which is, part Berry curvature, part quantum metric, and so you don't get like kind of a pure response of the quantum geometry in these sort of probes, but it's present. So we looked at some minimal models to see that the quantization here actually does reveal the charge of the Weil points. So that's a way to measure the charge of the Weil point through this second order response. And trying to address the question about the quantization, we did a comparison of these low energy models, which clearly produce the quantization. So focus on this curve here. So this is a quantized state. This is for n equals to 2, so it's a charge 2 Weil system. What I find interesting is that the first corrections to the linear dispersion of the Weil, that's the green curve, basically lies right on top of a tight binding model, which has like no low energy approximations at all. So 2-band tight binding model, and the leading corrections to the linear dispersion are quantitatively more or less indistinguishable, and there's a noticeable shift from just this linear dispersion. So one of the results I think that's interesting here is that small band corrections make significant improvements on the quantitative regions of where you would expect the quantization in a real model. But that's just a 2-band model. We went to a 4-band model, and basically once you have more than 2 bands, the quantization is gone. So even without interaction effects, disorder, or other kind of material imperfections that might be present, a 4-band model, which has more complicated mixing of states with the presence of the light, already destroys the quantization. So it's a very fragile quantization in this second order response. So the parameter delta here, the bigger it is, basically the farther away those higher energy bands are from the low energy bands that hopefully would be dominating the response. So there's some other things that we looked at. Turns out that you can determine basically the tilts, chemical potential, topological charge by doing enough sort of measurements with this nonlinear regime. So it's a way to circumvent photoemission limitations if you want to know the properties of your Weil dispersion. Okay, so motivated in part by the question of how much information about the quantum geometric tensor one can obtain from these second order responses, we looked at this topological superconductor, which I think is rather interesting. So tantalum disulfide is a very well studied material, but primarily in its 1T type, which has these Star of David sort of charge configurations with local moments centered on them, and the 1H polytype, which is more metallic, less correlated. This 4HB is an interleaving of the 1H and the 1T type, and its properties are somewhat different in the superconducting phase. And this nice set of STM experiments from the Weitzman group saw that near the boundaries of the system, particularly near step edges, where there's a change in the termination layer, there appeared to be a metallic edge mode. So the question was asked, well, is this metallic edge mode a signature of topological superconductivity or not? So we wanted to look at that question from the point of view of a different probe. So we looked at the nonlinear optical response, the second order response. There was a Hamiltonian for the system, which had been prior parameterized already in the literature. It contains pairing between even and odd parity states on site. So it's a mixed parity superconductor because it's broken inversion symmetry overall. And the Fiete diagram looks something like this. So alpha is the size of a spin orbit coupling term, and this parameter C is related to the mixing of the different singlet and triplet order parameters on site. So you have a phase diagram which includes time reversal invariant topological superconductivity. That's the tritops. There's a nodal superconducting phase and a trivial phase. The model assumes that all these phases preserve time reversal symmetry. And then we can compute the second order response. And essentially, it has a different frequency dependence that indicates which phase you're in. So as an experimentalist, you can basically just measure this frequency dependence and correlate it with the phase diagram and hopefully place your material in the phase diagram to either support, say, a topological state or not. So this is the cartoon. This is what the actual calculation looks like. And so you can see very similar features. In particular, sign changes are a very nice thing to look for beyond just the frequency dependence. OK, then the next topic, this rhombohedral trilayer graphene. So we've heard a little bit about this before. What we were interested in is applying a displacement field, which of course breaks the inversion symmetry, so we can have a finite nonlinear response. And we wanted to see if we could correlate changes in the optical conductivity as a function of frequency with band quantum geometry changes. So is there a way that we can kind of read it off? Can we read off changes in the quantum metric, or can we read off changes in the Berry curvature associated with the sign change? So we looked at this question in detail. Here's calculations of the quantum metric. Here's calculations of the Berry curvature. We overlaid it with joint density of states, which is convolved with those quantities, and tried to see if we can read off those changes in the second order response. And while you get a lot of information from the frequency dependence and the shapes of these curves, in the end it turns out that it's not an easy task, that you cannot easily just read off, okay, this is how the quantum metric has evolved by looking at the frequency dependence of the second order conductivity. So there's just too much which is convolved underneath the integral to get an accurate measurement. Okay, and then the final topic that I have, chiral phonons. So these are some of the interesting reasons that I think chiral phonons are interesting physical objects to look at. They can carry finite angular momentum. Therefore, they have systems which are somewhat analogous to spin systems. So there's a phonon-Zeeman effect, which is what I'll focus on. And the motions of the ions, if they're carrying finite angular momentum, also because they're charged, creates internal magnetic fields, and these could be potentially very large. So it's a way to create large internal magnetic fields in a material without the burden complications of having a large externally imposed magnetic field on the system. It also provides a mechanism to transfer the angular momentum of light to and from the lattice, or between spins in the lattice. The phonons can differ depending on where their low energy states arise, like whether they're near the zone center or near the zone boundary. And then there's a natural connection to topological electronic band structures with strong spin momentum locking. And there's this possibility to basically move angular momentum between all the degrees of freedom that you like. So spins, lattice, potentially like orbital degrees of freedom. And so there's a way to kind of transfer, store angular momentum in principle. And one of the recent experiments that I find quite appealing is the injection of a spin current into a heavy metal measured by Seebeck effect, inverse spin Hall voltage, by chiral phonons. So you have a non-magnetic material which you can apply either a temperature gradient to or drive it in the right way with light to create basically a current of angular momentum coming from the chiral phonons and then inject spin into some metallic state without having any magnetism in the system in the conventional sense, electronic-based magnetism. Okay, so chiral phonons with giant effective magnetic moments is what I'm going to focus on. If we look at how the magnetic field couples to the angular momentum, there's some coupling constant here, which is inversely proportional to the mass of the ion. So if we look at the splitting in a magnetic field for an ion which is circulating and compare it with the splitting that we would expect for an electron in a magnetic field, it should naively be down by a factor of a few thousand or more. That's for if the ion is just a proton, because many ions are heavier. So if one looks at various experiments, am I out of time already? Yeah, fine. Okay. Actually, no, you have to have questions. You're out of your regular time. Oh, okay. Great. So I'll wrap up in just a minute or two. So if we look at a few materials, this lead telluride, thermoelectric material, this one has a G factor, which is at least 2 or 3 orders of magnitude larger than the naive expectation, but still 1% or so of the electronic G factor. If one adds in tin and converts this material to a topological crystalline insulator, so for large enough X, somehow that topological band transition leads to a G factor, which is suddenly of order the electron G factor. So there's a huge boost associated with this topological band transition. It turns out you can capture that physics with a band theory model that takes into account the topology. And then the final system that I'll talk about is this cobalt titanate. This is the Dirac-magnons that I mentioned. Just to sketch the model, if you take into account the orbital structure, the d orbitals of the titanium in this, and look at how those electronic states are coupled to the phonon modes, the very weak spin-orbit coupling in the material splits the levels to the same energy scale as the phonon modes. And so that matching of spin-orbit coupled split modes and the phonons basically produce in this material a G factor, which is of order the electron G factor. And we've worked out the details of that effect, and we can produce something which is in very good agreement with experiment. And so I'll kind of skip this. There's interesting physics in chiral phonons, which I mentioned, and then finish here to thank all of the collaborators on this project, and then I'm happy to take any questions. Thanks so much.
We have time for questions.
Yeah.
Yeah, so I wonder, this is very interesting. So near the topological, when you go to topological side, the electron wave function is spread out between the cation and anion. I wonder if that helps increasing this chiral phonon effect. In other words, the electron is no longer very purely localized on one type of orbitals, but it spreads between different atoms.
Yeah, so I think that's a good thought. So we didn't look in that level of detail to see like how the wave function spread is influencing the G factor, but that intuition sounds quite reasonable to me.
Yeah, we can chat more. Quick question is, how is this phonon, chiral phonon G factor, how is that measured?
How is it measured?
Yeah.
So basically, they look at the magnetic field dependent
of the phonon frequency?
Yeah, of the phonon frequency, essentially. So.
And this is the zone center phonon?
Yes.
Okay, thank you.
Thank you for your talk. I have a kind of a dumb question concerning chromium iodide.
Okay. I doubt it's dumb. But.
It's known that chromium is a good flexomagnetic material. Like, did you include in your model this kind of inhomogeneous strain, basically caused by deflection or torsion?
So no, that we did not include inhomogeneous strain. So we basically identified the normal modes. So the sort of distortions that we took into account were the normal modes of the system. So those oscillations, and it was just the shear mode for this chromium triiodide. So it's shown here. This is the one. So the two layers are shearing this way. So the arrows, I don't know if you can see it from the back, but the little yellow arrows here are indicating basically the motions of the atoms in this shear mode. And this is, in the calculation, we just focused on this one particular sort of motion. We said, if that's the only thing happening, just that kind of shearing motion, then what would the changes in the exchange constants be?
Okay.
Yeah.
Okay. Because if you include, for example, because as far as I remember from chromium iodide from a paper like 2-3 years ago, when they basically calculated the flexomagnetic properties, they had to include this kind of bending modes in order, and also the gradient of the strain in order to englobe all these kind of properties.
Yeah.
Thank you.
So I think that that's certainly a way that one could improve upon these calculations. So our perspective was, well, this is kind of like a minimal study, so we can see what the dominant expectations are. And I don't know if anyone has attempted this experiment. This work is about 4 years old now. But it should be simple, because all you have to do is some kind of optical experiment which is sensitive to, like, zero magnetism versus finite magnetism, and like Kerr effect, Faraday effect, or something. It should be, in my imagination, an easy experiment. But I don't know. Someone like Peter could tell me if that's correct or not.
All right, let's thank Gregory again.
Thank you.
Okay, so plan change. I think it's better to do the group photo right now before it's going too dark. So let's go outside the building, and it's about 3 minutes walking in the north direction along the main street. So let's take a photo in front of the so-called Thompson Hall.